The real title of this talk might be this, but that just seemed a little too aggressive to put on the actual front slide that would sit there for a long time. But like, why would anybody care about fusion given how cheap solar power is at the moment? Aren't we done already? So I'll tell you a little bit about how I came to fusion from being a software engineer, and then why I decided that fusion is useful to work on, spend time on, support, that kind of thing. A little bit why fusion is something that you might take seriously now after a long time of being ignored, and then talk about what it takes from fusion to get from where it is now to reality, to delivering power onto the grid, and what sort of numbers it has to hit, because it's sometimes thought of as, oh, we'll just get fusion and it'll be too cheap to meter and it'll be wonderful. And the reality is a little bit more complicated. So I was a software engineer for a long time. I worked at a failed virtual world company. I wrote a lot of the first version of Gmail for Android. And especially while I was at Google, I was not especially happy. I seriously considered trying to become a Navy SEAL or a bounty hunter. It's fair to say I lacked some direction. I just eventually aged out of being able to become a Navy SEAL before I realized that I just needed to lie and say that I was gay, and then I could have solved a whole bunch of the problems that were holding me back from that line of work. I thought about starting a porn website, and in the end didn't do that either, and instead was the first employee at Asana. And that was really the beginning of a shift for me, because that the company has very strong values around positively impacting the world that I gradually absorbed. So I went from, hey, toss up between porn company or joining Asana, to 6 years later saying, working on a company that is trying to improve the efficiency of human collaboration isn't enough for me. Instead, what can I do about climate change directly? And the second part of how I got there was that in 2015, I read 3 different things that really propelled me from, hey, collaboration is cool, to climate change. One of those is this somewhat dated at this point book, Sustainable Energy Without the Hot Air by David McKay. He was a computer scientist who was frustrated by how few numbers are involved in most discussions about sustainable energy. So for example, people will say, oh, we can make so much energy by putting wind turbines off the north shore of the UK, so clearly we should do that. And then he would come along and say, well, this is how much energy you can make in the best case if you do that. And by the way, this is how much energy we use, and look at how these numbers really, really don't compare. So the book is a wonderful walkthrough of how energy can be made from renewable or other clean sources and how we use it. And the primary takeaway that I took from this was these numbers are on basically different orders of magnitude. It's very difficult to see how we can build a complete energy system from just renewable sources. An Eco-Modernist Manifesto is from a bunch of primarily Bay Area people, like the ones behind the lawn now, and there's this full-throated plea to think about how density and improved technology, and in many cases big technology, can get us to places that we'd actually like to be and that we will struggle to get to if we just take this back to nature, back to basics approach. But arguably the thing that had the biggest impact on me was a series of blog posts on the blog Wait But Why. If you don't know it, it's written by a serial procrastinator, which means that once it became his full-time job, he stopped writing it because he then, I guess, found ways to procrastinate writing it. But before that, he did a wonderful series of posts based on embedded interviews with Elon Musk. And through this, I discovered that the story of how the world got SpaceX is significantly more complicated than I thought. Basically, Elon Musk was really determined that humanity should become a multi-planetary species. But the only role that he saw for himself in how to accomplish this was to try to do a mission to Mars that would land some equipment that would put a plant inside a dome on Mars, which would then grow with a webcam watching it, so that humans on Earth would look at all of this and say, oh, life on Mars is possible. NASA should have more money, and then ... Eventually, NASA would send humans to Mars, and then a century later or whatever would be a multiplanetary species. And so Elon Musk really tried to do it this way until the Russians, who he tried to buy the rockets from, spat in his face and told him that $20 million was not enough money. And it was only after that that he was flying home and wondering why on earth rockets were so expensive that he started down the journey that led to him starting SpaceX. And of course, what we discovered from this is Elon Musk, by all accounts, extremely intelligent, extremely capable, was actually insufficiently arrogant. Even he underestimated his own abilities. So I said, well, what would I do if I could not fail? Or the slightly more humble version, at least what's worth failing at? What would be good to try here in the area of climate change? And I figured, well, I'm a software engineer. It's really all I know. So maybe there's a way that I can write some software, help people with clean energy stuff. And as I looked more into the clean energy space, I discovered that I just don't see a way to move the needle through software engineering. Instead, as a side project, I thought, while I was still looking for ways to contribute as a software engineer, I discovered that fusion was more exciting than I'd realized, and I'll explain why in the next few slides, and that a small amount of money could help quite a number of fusion companies. So I found a rich person who was willing to put some money in, and he told me, but Malcolm, there's no way I'm going to give money to these companies directly. They're going to come back to me to be on their board. They're going to come back to me when they want more money. Like, no fucking way. You have to start a VC fund. So that's how I became, as far as I know, still the only venture capitalist with a fund entirely focused on fusion companies. So I did that. One of the companies did quite well. The other companies kind of fizzled, but maybe 1 out of 4 is not so bad. Then I failed, really putting the truth to what's worth failing at. I completely failed to raise a second fund. I think that part of this was I didn't have the right team. Part of it is a fusion fund actually doesn't make a whole lot of sense. It doesn't have a lot of portfolio diversity. Anyway, so I said, well, maybe the time's not yet right for a fusion fund. Who knows? But I'll go and work at ARPA-e. For those of you who don't know ARPA-e, it's basically the DOE's form of DARPA. So ARPA-e gives money to companies or national labs or universities that are researching early stage, potentially disruptive energy technology. Okay. And I did tech to market for a year there, working on supporting fusion companies. So saying, assume that fusion technology works, what else can we be doing to help these companies become successful in the market? So why did I decide that fusion was worth spending my time on? At the root of all of this, at the root of all of the clean energy conversation, I think, is the need to get clean energy from about 10% of the world's current energy demands to 200%. The reason it's more than 100% is we have population growth, we have people hopefully getting wealthier and using more energy, we have electrification, so a bunch of things that are run directly off heat at the moment because we burn fossil fuels will need to be run off electricity. So in some cases that will use more energy. In some cases like cars, it uses less energy. And then we're likely to have, we already have more CO2 in the atmosphere than we can keep there. It's not just that we need to stop our current emissions. We need to take CO2 that's in the atmosphere already out of the atmosphere. That's going to take a whole lot of energy. So super rough numbers, we need to get clean energy from 10% to 200%. The problem is that decarbonizing energy using just renewables is really expensive. What this chart shows us is the cost of getting the grams of CO2 per kilowatt hour of electricity that we produce down. So as we bring it down from 500 grams to 1 gram, you can see the cost rising, but the cost rises much more if you're in this orange scenario, which is no nuclear power. And this is true in a whole lot of regions of the world that people have looked at. I've just shown one from America and one from China here, but this is generally true. And the reason for this is that while hydropower is really cheap, it's not scalable. We've basically dammed all the rivers that we can dam, and then actually freak heat waves become more common, and they mean that even the hydropower that has been pretty reliable has to get turned off, and we're seeing that now. But the ways that we can scale renewable energy are primarily through wind and solar, and those are intermittent power, meaning that we need to do extra work to turn them into something reliable that we can run a grid off. So we can time shift the electricity that we generate this way through batteries or other storage. We can space shift it through long distance transmission. And of course, we can manage demand. The approach that people talk about the most, though, is time shifting with storage. And the problem there is that storage needs to be way, way cheaper than it is on track to be in order for this to work. So on the left here, I show the current cost of the electricity system as the baseline in black. So that's about 4 cents per kilowatt hour for wholesale prices. And then green shows the cost of system-wide energy. That's the system levelized cost of electricity as a function of the cost of storage. Now, if you look on the right, you can see what batteries cost at the moment, where they're projected to come down to $182 per kilowatt hour. So they've come down away from the 300 at the very left of the chart on the left, but they're nowhere on track to get down to $10, $1, or a tenth of a dollar, at 10 cents, which would even then leave renewable grids at a significant price premium over the grid that we have today. So at this point, a lot of people are like, look, dummies, we all know that lithium-ion batteries are not the cheapest way to store electricity. Don't price this out as the solution, price out hydro. So fortunately, people have done that, but they didn't really get to the point of pricing it because it really just doesn't look as if you can scale hydro storage far enough. The idea here, though, is that it is much cheaper to store electricity or energy by pumping water up a hill and then allowing it to flow down the hill again to get the electricity back out or get the energy back out. So this blog here, Do the Math, worked through this. The assumption is that you need to store about 7 days of energy for the US to make a renewable grid work completely. And this requires 170 really immensely large dams, each one twice the height of the Hoover Dam, each one with 60 times the power of the largest project that we've ever done, with as much concrete as Three Gorges plus Grand Coulee. They'll cover a huge area. They'll take a whole lot of water. We don't have this water. And if you're like, look, these dams are crazy large, we should do smaller ones. Nonlinear scaling means you need far more dams, far more concrete, far more water to make this work. So I look at all of this and I say, by all means, keep building wind, keep building solar, do storage, whatever you want. I don't think we're going to solve the problem this way.
Malcolm. Super quick. Sorry, I'll just jump in for a sec. That blog, the key insight for me as to, like, gave me an idea of like why this is true as opposed to like lithium ion is that essentially 100 kilograms up 10 meters is the same energy storage as like a AA battery. Right, yep. Because the volumes involved in that, you know, you kind of have the potential energy. So if you have, you know, tall mountains like the Himalayas nearby, you're doing great. And if you don't, then, you know, you basically kill yourself on concrete costs.
Yeah, great point. And then, of course, water is not that heavy. So you can look at using heavier materials, but the really heavy materials are really expensive. And if it's not water, like maybe you can get a factor of 3 in density, but it doesn't really change the numbers here. And if it's not a liquid, then it's much, much harder to move it around.
Malcolm, if you go back to the lithium versus LCOE chart, are you proposing that that the numbers in dollars per kilowatt hour should be compared directly storage versus LCOE, or like what kind of assumptions are you using to like transpose, or what sort of assumptions are you trying to use to like make those two numbers comparable?
No, it's not a direct comparison,
Okay.
of course.
Yeah.
This is from this study here, if you can see my mouse, analyzing energy technologies and policies using DOSCO. So Google's research/energy division, which I think Olga used to work in, wrote the simulation of the US energy grid, where they look at renewable supply and demand, and then they can put on nuclear, coal, gas, that kind of thing, as well as storage. And they can also constrain which energy sources the system is allowed to use. And so in this particular run, they're looking at only renewables, and then they're doing a sweep of across the price range for storage to see how the system's cost of energy is a function of this cost of storage.
Thanks.
Yeah, it is a very short, very readable paper, which I highly recommend. It really changed my thinking about this. Okay, so I'm not the only one to look at this and say, trying to solve the energy problems by just going after renewables and storage looks untenable. This is Saul Griffith's Sankey diagram. It shows very broadly how energy flows through the economy. And Saul likes to say, no, of course we're not going to do it with renewables and storage alone. We just need to solve transportation, heating, buildings, et cetera, like 6 different areas. And yeah, by the way, each one of these is 1,000 separate teeny little lines here that we need to address. So you can do that. And I think there's a lot of merit to going after these different areas, because as many people will point out, often you can save money by doing this. So we should be doing it anyway, or it's very cheap and it reduces the amount of energy that we need to use. So it reduces the amount of energy that we need to replace, energy capacity that we need to replace. But 6,000 separate problems sound intimidating to me. And you don't get to zero by making all of these little pipelines on this chart smaller. We need to get to zero, and then we need to get well below zero. So my contention is that a necessary part of the solution, perhaps sufficient, perhaps not, but definitely necessary, is clean, cheap, abundant, safe energy and zero carbon fuels, because there's no way that we're going to replace all of the vehicles, especially long-range aircraft, that kind of thing, with electric versions in the time frame that we need. So zero carbon fuels, where we use probably electricity or clean heat to make fuels from carbon that we have captured from the atmosphere. Direct air capture, because as I said, we already have too much CO2 in the atmosphere, and we're not going to manage to decarbonize all the parts of industry. And then geoengineering. I think we have to do all 4 of these. They're all going to take lots of energy. And if we go and crank down on the little parts of this problem, that's great. That makes this easier, but we have to do this. So what options do we have for clean, cheap, abundant, safe energy? Noting that we need that for primary uses of energy, and we need it to run the zero carbon fuels and the direct air capture and the geoengineering. So the root of all problems, I believe. And we don't have great options here. We have wind and solar with storage, but I've just been talking about the problems there. We can try to put carbon capture and sequestration on fossil fuels, but they don't get us down to zero. And there are a whole lot of other problems with fossil fuels. We have fission, which I actually like. I'd like people to build more fission, but good luck with that. The public and the regulators and the investors all seem pretty unhappy about that. And then we have fusion, which looks great until you look at the bottom row and you're like, oh, cool. fusion is the only energy source that we talk about that has to have quotes around source, because we have never produced more energy from fusion than we have put in. So starting from behind, and that gets us to the next section, which is, isn't fusion science fiction, or aren't people right when they say fusion's always 30 years away, or is 30 years away and always will be? And the answer, I believe, is no. What's that, someone? No, just, I can't tell. Is it background noise, or are you talking to me? Just background noise, okay. So I'll explain why I think fusion is interesting and actually actually real. Oh yeah, can you mute people or do something?
Yeah, I'm just trying to figure out who it's coming from.
Just mute everyone and they can unmute if they want to.
It's a good idea.
I think it's Margaret Parker.
But also just mute everyone.
All right.
Okay. Right. So if anyone here doesn't know, I'll just briefly remind you what fusion is. Nuclear fission is where you take a heavy, unstable atom like uranium and you split it into two. And in that split, you get neutrons that come out, and you can use those neutrons to heat something like water and then drive a steam turbine. Nuclear fusion is the opposite in some ways and then identical after that. With nuclear fusion, you get stuff really hot and dense so that two atoms fuse into one, and then you get some byproducts that come out like helium in this case, and then neutrons. And then after that, it's the same. The neutrons heat up eventually water or CO2 or something like that and drive a turbine, and then we make electricity. And we'll come back to this a little bit later, but the easiest way of doing fusion is to fuse deuterium and tritium that are both isotopes of hydrogen. So they have the proton that hydrogen has, and then they have one or two neutrons in the nucleus in addition to hydrogen, in addition to the proton. So in spite of the public perception that we haven't made any progress on fusion in 60 years of trying, you can look not at whether we now have fusion that works, which is a pretty binary description, but rather how much energy are we getting out of fusion over the energy that we've been putting in to make the fusion happen. And if you do that, then you see that since 1970, fusion gain, as this is called, has been going up exponentially, and indeed going up faster than Moore's law was improving CPUs. The problem is that this chart doesn't show the cost of all these fusion experiments. Basically, the cost was going up logarithmically as well. This was okay, sorry, exponentially. This was okay for the fabrication plants that make the chips that were defining Moore's law, because those were business units that actually made a profit. When all of this is publicly funded fusion research, this gets painful. So back in 1976, people looked at a bunch of different hypothetical pathways for how we might get fusion energy. And there was the really expensive blue line at the top that was going to get us it fairly quickly, and then various approaches that involved funding at a lower rate that were still expected to get to fusion. And then there was the line that they called fusion never, which was the red line. And then we didn't even do the level of funding that was fusion never. We did the black line that was even less funding for fusion than that. And so when you think of it like that, it's actually quite impressive that fusion continued to track on this exponential improvement scale, given that it was getting the black funding. Even so, people were getting pretty disgruntled about fusion. More recently, meaning since 2005, 2010, that kind of thing, a bunch of disruptive changes have combined to create a very different landscape for fusion. Some of these actually go back a little further. So as I said earlier, fusion requires getting gas typically very hot and very densely packed, and then leaving it there for long enough. So we're looking for this combination of density, pressure and density, temperature, and confinement time. So the biggest fusion project in the world at the moment is ITER, I-T-E-R, which is a worldwide collaboration being built in France. It's expected to cost tens of billions of dollars and take many decades. Even that thing, which I consider to be of dubious value, like it's not clearly focused on producing energy in a way that is at all relevant to the world. Even that was only possible to the extent that it is working because while ITER was being designed, magnets got better and they were able to make ITER considerably smaller and cheaper than it would otherwise have been. The idea is that with stronger magnets, you can compress your gas or your plasma more, and so you can make everything smaller and hence cheaper by having better magnets. Better software means that we can better model what's going on in the plasma as we're squeezing it and heating it, and try to keep it stable for longer without having to do all these experiments. Better computers mean that we can run the better software faster and try a whole lot more things. Perhaps one of the most important shifts recently has been that we went from doing fusion, saying kind of that we were doing it for energy, but really doing it for science or for weapons, to focusing on energy. So 15 years ago, there were two main fusion projects in the world. One was ITER that I mentioned in France, and the other one was the National Ignition Facility, which is in the Bay Area at Lawrence Livermore. So ITER is really a science project. The National Ignition Facility, or NIF, is really a weapons project. By doing fusion research, especially in the particular configuration that they've chosen, they can study the conditions that go on in hydrogen bombs without actually violating the Test Ban Treaty. NIF has been described to me as the perfect energy research facility, where perfect means, if you're a really cynical DoD type person, it means it's big enough that the people that you have working there can tell themselves that if they just work harder, delay retirement, dedicate themselves more, then maybe they'll get to energy gain. But it's small enough that it'll never happen, and you can keep on milking these people for weapons research. So when you start with that as the backdrop, the fact that we now have a host of companies, which I'll talk about soon, that are dead set on using fusion to deliver energy on the grid at a relevant price point and soon enough to matter for climate change is a huge shift. Related to that, ARPA-e changed the funding situation in the US. The funding constraints that we'd seen before meant that fewer and fewer projects were getting funded until it was only one approach that was getting any money. ARPA-e came along and said, that approach is clearly not working. Let's put tiny amounts of money, like a few $1 million, into a host of other approaches and see what happens. And I think it's fair to say that that enabled a lot of other exciting approaches to make progress, and that catalyzed a lot of the private money that is going into fusion now. So let me tell you about a few of the more exciting companies that are in fusion at the moment. By far the highest profile of these at the moment is Commonwealth Fusion. They're a spin-out from MIT, from the nuclear science and engineering department there. And what happened was a prior funding cut meant that all of the funding for their lab was going to be killed. They weren't even given money to wind down their lab. So they went out swinging hard, raised private money, and spun out this company. Another fundamental part of this is that they said, what can we do if we look at the magnet technology that is coming out at the moment? And what they realized is that magnets that are even better than those that are being used in ITER mean that you can make your tokamak, which is a donut configuration of plasma, half the radius again from what ITER is doing, which means that all of your costs come down by 1/8. And then suddenly everything looks way more tractable. Another advantage that they have is that they're using high temperature superconducting magnets, which mean that you can actually break apart the conductor that forms this electromagnet and then open up your plant, service it on the inside, and then combine the two halves of your conductor again. You can't do this with a regular superconductor because that junction where the two different pieces of superconductor meet is not superconducting and will make enough heat that the entire conductor will not be cold enough. And then you get normal resistance and no superconductivity at that point. So they observed that through stronger magnets and higher temperature superconductors, they could make a design that looked quite practical. They raised hundreds of millions of dollars around this concept, and they think that they're on track to demonstrate energy break-even around 2026, I believe, something in that time frame. I'm not sure I believe them, but they're very excited, and I'm excited that they have enough money to make a solid try at this. There's also a variant of a tokamak, which is a stellarator. A tokamak has regular magnets all the way around the donut of plasma. It has a regular magnetic field. It's very simple to think, it is comparatively simple to think about computationally, but it requires lots of magnets in different places. You have the magnets that are going around the donut, and then other magnets that are sitting on top of and underneath the donut, complicated heating systems, complicated hardware to detect when it is becoming unstable and keep it stable through active response, that kind of thing. Stellarators are conceptually simpler, but also fiendishly complicated. They have this highly irregular coil structure around them and a very irregular asymmetric magnetic field. But the result is something that doesn't need as much external heating, doesn't need active stabilization. And this was an idea that originated in the 60s, around the same time as tokamaks. And then tokamaks looked quite promising, and people just couldn't figure out the computational side of stellarators. So all of the attention shifted to tokamaks. Much more recently, people have built a stellarator in Germany and verified that it actually works the way theory suggests. And then secondly, our improved software capabilities mean that we can much better model what magnets we need to put where in order to get the magnetic field that we want. And then the really new part of all of this is part 3, where people take two different approaches. One says, normally, these weirdly shaped pieces here are quite difficult to make. They're very difficult to make. You have to precisely bend a superconductor to within 1% of the shape that you modeled out, or you don't get the magnetic field that you wanted. But superconductors are really finicky. Like if you bang them a little bit hard, they stop being superconductors. So it's this incredibly complicated and expensive fabrication process. So one approach says, let's 3D print these things, because then we can just make much larger pieces that are exactly the shape that we want, and then we'll just drop them together and we'll get our stellarator. Another project says, actually, if you crunch the numbers even more in your software, you can figure out where to just place permanent magnets on this and ditch all of the superconductors. So you don't have these complicated superconductor curves here. You just place ordinary permanent magnets in very carefully chosen locations, and you get the magnetic field that you want. So these things were definitely laggards in the fusion race for a long time, and there's some really exciting stuff happening there now. Heading further along the spectrum from very conventional fusion to very crazy fusion, we have companies like Zap Energy working on Z-pinches. The idea here is that if you run current down two parallel conductors, the magnetic and electric fields that are created by that will pull the conductors together. Plasma is a conductor because plasma is what you get when you make a gas hot enough that the nuclei and electrons are so energetic that the electrons no longer stay in orbit around the nuclei. So it's a good conductor because the electrons can just move freely. So you can then have a column of plasma, run current down it. The plasma will squeeze in radially. The more it squeezes, the higher density of current you have in terms of current per unit area, because the cross-sectional area is declining. So you get an even stronger electric and magnetic field, and you get this positive feedback loop compressing the plasma. That same positive feedback loop makes the plasma unstable. If you have any irregularities in your initial conditions, then the plasma can buckle, kink, and break the circuit, and then it's all over. So ZAP appears to have found a really neat way of stabilizing the plasma during this compression by having it flow at different speeds down the column of plasma, and then that flow stabilizes it. So they call this shear flow stabilization. And very excitingly, they just completed a fundraising round on the order of $30 million. So for a long time, it's like, guys, go faster, would you? And now they have all the money they need to really go fast. So they claim that they are also within 5 years, and I'm rounding up in case they think that the actual number is secret, but within 5 years of demonstrating energy gain. Then we have general fusion, which actually uses steampunk-style pistons to compress a spinning liquid metal liner that then compresses the plasma on the inside. An advantage of both this design and ZAP, which would also have a liquid metal liner, is that you don't have the neutrons collecting or going through a solid metal wall surrounding the plasma. You have the plasma directly touching the liquid metal liner, which means that the neutrons are not damaging a durable part of your reactor. General Fusion has, in the last year or so, I think raised $300 million, and we'll see how they go. A lot of people are somewhat skeptical, but again, they have enough money that we're going to get to see what happens there. More secretive still, we have Helion. In this particular case or design, they fire plasma in from both ends of this conical structure. They have a special configuration of plasma called the field reversed configuration, or FRC. This is a configuration of plasma that stays stable for longer than normal plasma does. Stable means it doesn't just belch the energy out and cool down, it actually stays hot and stays as a plasma for longer because it's trapping the energy. What's really neat about an FRC is that it's a roughly cylindrical shape, and if you squeeze it radially, it doesn't get longer along the axis of the cylinder, it gets shorter as well. So you can, and there's another neat thing about FRCs, which is you can merge them. So you can fire two at each other from opposite ends, and then if you do this right, they'll merge into one FRC in the middle. So they fire an FRC in from each end, and then these coils down the cone there on each side, as the FRC comes by, turn on and create a magnetic field that squeezes it, and then it gets to a smaller part of the cone, and then the next magnetic coils fire and squeeze it some more, and then they meet in the middle, and then no one agrees on what happens next. The company says things are going great. There are rumors that I certainly haven't heard directly from anyone at the company, but nevertheless, rumors going back several years that they are just about to demonstrate energy gain, and their investors seem very happy. It's possible that they've already demonstrated energy gain and they're sitting on top of a secret that they're keeping incredibly effectively. It's possible they're really close to energy gain. It's possible they think they're close to energy gain and that their skeptics outside the company are right. Really hard to know because they don't publish and they don't talk. And then we get to, okay, not the craziest. The craziest type of fusion is cold fusion, but I'm going to stick to fusion that there's actually theory for. Muon-catalyzed fusion is cold-ish fusion that there is theory for. The idea here is that normally it is difficult to fuse atoms or nuclei because nuclei are positively charged, so the positive charges repel. And so you have to do a lot of work to get these things close enough before the strong atomic force, which is what pulls nucleic particles together, can take over and pull them together. A muon is just like an electron, except it weighs 200 times as much, and its half-life is 1.5 microseconds. So if you can replace some of the electrons in your plasma with muons, then because they're a lot heavier, they orbit much more closely to the nucleus, which means that you can get the nucleuses a lot closer before the positive charges of the protons in the nucleus are pushing each other apart. And so it's a lot easier to get to fusion. Muon-catalyzed fusion is something people have been excited about for a long time, but the problem is that it's energetically expensive to make muons. The muons don't last for very long, and they stick. In about 1% of cases where you fuse two things, the muons don't just go flying off ready to catalyze more fusion. They instead come out in the hydrogen that comes out when you've done your fusion. And then by the time they unstick from the hydrogen, they've died because they don't live very long. So people are pushing on two different aspects of muon-catalyzed fusion. One is, can we make muons with less energy invested so that the existing stick rate that we get is energetically acceptable? The other observes that we have a theory for the stick rate and the unstick rate for muons, and then we have some experimental data. And the experimental data actually doesn't match the theory very well. And it's about the one time in fusion where you're ever going to hear this. In this case, the theory is more pessimistic than the experimental results. So ARPA-e gave a company $800,000 or so. It was a small award to do more experiments. And the idea is, hey, maybe the theory is actually wrong. Maybe the experimental results are right. And we just need to go to higher temperatures, higher pressures, or other ways tweak the system just right. And then we can make muon-catalyzed fusion work. So the basic roadmap to fusion here is we need to get to energy gain. Maybe Helion's already there. Otherwise, we're somewhere between a few years and 10 years from getting to energy gain. Then we have a whole host of engineering problems that we need to solve before we can build a plant around this. Ideally, we'll do this in parallel, but if we're dumb or pessimistic or something, then we'll wait until we've actually demonstrated fusion before we do this. These problems are things like, if we have a design that has a solid first wall between the plasma and the molten salt that is collecting the neutrons, working on materials that can survive the neutrons that go from the plasma to the molten salt, working on better superconducting magnets, working on things that can separate the tritium out from all the other waste products that come out of the fusion so that we can recycle and reuse that. A whole host of problems. The DOE and ARPA-e are working on some of these. Some of the more bold and far-sighted companies like Commonwealth are working on these, but we are not doing nearly enough on there. And then we need to build an initial plant. So companies, the most aggressive companies, believe that they're going to get the initial plant on the grid in 14 years at this point. I think that's optimistic, but at least if we did a Manhattan-style project, really concerted push on this, it's possibly possible. Anyway, somewhere around there is the aggressive time frame that we're looking at. And that brings us to the final part of this. Is there actually a market for fusion if and when it becomes a possible option? And if so, what does that market look like? While I was at ARPA-e, I and two other people wrote a report on what possible markets fusion should be going after. You can really think of this, though, as if I have a magic new heat source, if I have a magic new firm heat source, it doesn't fluctuate the way renewables do, what are the markets for that? What prices do I need to come in at in order to have a market? People get pretty excited about using fusion or these other energy sources first for industrial heat, or process heat as it's called. We actually think that the most promising initial market is electricity. The reason for this is if you're making heat to sell to a customer, you can't move heat very far. You can run it down a pipe that you have steam in or something like that, but you can sell it to the building next door if you're lucky. You can't sell it onto the heat grid through all of California, for example. And so you're really dependent on a neighboring facility or being part of a large facility in order to have a market for heat. Another market that people are really excited about is using energy from fusion or fission, if they're in that camp, to run electrolysis equipment to separate water into hydrogen and oxygen, and then forget about the oxygen. The point is to use the hydrogen to make, for industrial purposes, or to make ammonia or methane and make a whole bunch of hydrocarbon-based fuels from that point. The problem with that market is it's really a global market in most cases. Because it is easy enough to transport the final product around, you're competing with the lowest product and the lowest cost producer anywhere in the world. By contrast, electricity is a regional product. You can make it, you can sell it onto a grid that is reasonably large, you're not dependent on a customer right next door to you, but equally, if you're selling on the grid in Europe, you're not competing with the cost of energy in Texas. And this is indeed what we see here. And remember, the US wholesale price is roughly 4 cents or $40 per kilowatt hour, but in Singapore, it is $110, per megawatt hour, not kilowatt hour. It's $110 per megawatt hour in Singapore, almost as much in Japan, and in a large part of Europe, it's over $50 per megawatt hour. This difference between the costs in most of America and the numbers here might well be enough to control whether early fusion reactors are profitable. There's something I should have said at the beginning of this section. In the long run, I believe that fusion should be the cheapest and in many ways best energy source that we have. The reason for that is it is the most energy dense energy source. So you can produce the most energy per area of land that you choose to use or per unit of mass that is involved. So if we build enough fusion power plants and we build them competently, we build them at scale, the price should come down on similar curves to what we've seen with wind, solar, batteries, etc. And there's reason to believe that it should be really, really cheap. Initial versions of fusion, though, are not going to be cheap. They're going to be challenged commercially in the same way that wind and solar and batteries all were early in their cost curve. So this is all about where can fusion start? What markets are less price sensitive and as such can support higher prices for fusion? Another reason that we think that electricity is a good first market is that electricity is a market where people will pay more for reliable energy. If you're running industrial equipment off renewable energy, and sometimes you're not producing electricity because the wind isn't blowing and the sun's not shining on you and that kind of thing, then that's just an economic decision. How much does it cost to turn my equipment off for a little bit versus install more batteries or something like that? Whereas consumers actually just want reliable energy. They don't want to have to put a price on that. So that's why we think that electricity is a great first market for fusion. However, by the time a fusion power plant might come online in 2035 or a little bit later, there's going to be a lot of renewable power on the grid. And the problem there is that renewable power costs almost nothing at certain times of the day. That's, for example, around the middle of the day here, where we're producing a lot of solar power and the aggregate demand for electricity is not that high. So if you run a fusion power plant or any magical heat source all day, no one's going to want to buy your product during the middle of the day because you need to charge more than $0 for your power. Fusion companies often just don't understand this problem. They're like, hey, unlike nuclear fission, we're technically capable of ramping up and down, so it's going to be great. We're just going to ramp our fusion power plant down when renewables are producing a lot of power, and then we'll turn it on again in the afternoon. We'll turn it on in these two white peaks here. And what could go wrong? And what can go wrong is at some point they'll discover that they haven't run their math properly. Specifically, fusion and fission are both dominated by the capital costs of the equipment. It costs a lot to build the thing, and it doesn't cost very much to run the thing. Meaning if you turn it off, you're not saving that much money. So 80% of the cost of a nuclear fission power plant, of the entire cost of electricity, is from building it. By contrast, 80% of the cost of a gas plant is from running it. So gas plants can turn on and off throughout the day to complement the renewables just fine, and they save a whole lot of money when they turn off. Fission power plants and probably fusion power plants don't have that luxury. So we think that anybody trying to integrate on a grid with a lot of renewables needs to think much more carefully about this, and probably needs to use thermal energy storage. So instead of ramping up and down their energy production, they would run that constantly throughout the day. And when no one's buying energy that they're producing, they will use that energy to heat up their thermal energy storage.
Malcolm, there's a question about the temperature range of heat from fusion that I think is relevant for the slide.
We don't really know, and it's one of the issues that I'll get to on the next slide, holding fusion back from being used for industrial heat. It depends a lot on what molten salt the energy is going into, among other things, also just what materials are holding that molten salt. You only need to get to, I think, about 600 C in order for this sort of thermal energy storage to work. So we think this is doable, but we're not sure how high fusion can go. So the idea would be store the energy when no one's buying it, and then when people do want to buy it, run your turbine at twice the power rating, so that you're drawing heat from storage and from what you're producing. And if you do that, you come in with a much more competitive cost of electricity. Longer term, we think that the cost of electricity that you produce from fusion needs to compete with gas, with the cost of electricity from gas. This is a function of the cost of gas, the price of a carbon tax, if there is one, and whether the gas is using carbon capture and sequestration. But if you're coming in at $50 per megawatt hour, which is this point on the y-axis, then you can compete with any gas system that costs more than $6 per MMBTU, which is a lot of the world. And if there's any CCS or carbon tax on top of that, then more of these lines get about $50 per megawatt hour. So we think that there's a large long-term market for fusion if it can come down to about $50 a megawatt hour. As I've said already, process heat is a tough market because you have to sell to your neighbor, and they might not care if they don't always get heat from some other sources. The exception is mines. Mining sites are often remote and pay very high prices to get fossil fuel energy out to the mine. And so fusion might do very well there because the price that you need to compete with is much higher. And on top of that, they're tolerant of downtime because they already have all of their diesel or whatnot set up there. And then if a fusion company installs at a mine and it goes well, the same company that owns that mine typically owns a lot of other mines and can be expected to roll out more fusion plants pretty promptly after that. As I said, hydrogen is another market that people get excited about. We don't buy it. One of the problems is that electrolysis equipment to produce hydrogen is not that expensive. So in some cases, it's cost effective just to turn the electrolysis equipment off when you're not getting energy from renewables. And the result is that fusion would need to produce electricity at $32 per megawatt hour or below in order to compete with renewables plus an electrolyzer. And that's just a really low bar to aim for. Another problem is that the downstream products that are made with hydrogen are often made through integrated processes with the production of hydrogen. So if you're producing methane, for example, it's an endothermic process to get hydrogen out of natural gas. Sorry, when I said methane, I meant methanol. It's an endothermic process to get hydrogen out of natural gas, and it's an exothermic process to produce methanol out of hydrogen plus the other bits and pieces. So people run this all together, where the heat from one process that comes out of one process is powering the other process. And the result is that they're paying effectively even less for their energy or their hydrogen than the numbers I just gave you. So it's even more difficult to compete with this. In the short term, there's arguably an early market providing absurdly expensive hydrogen to Japan and Europe to mix into to natural gas pipelines, because you can mix up to 15% hydrogen in with natural gas without changing the pipes or the stoves or the boilers or anything hooked up to this. I think this is really short term and totally incompatible with fusion's timeline, because eventually I expect that renewables are going to do this more cheaply. So that's the end of the talk. We should be looking at fusion because there's not a slam dunk option for decarbonizing energy. Fusion's progress is widely underappreciated, and it's experiencing significant positive technological disruption at the moment. Private companies are really capitalizing on this and hoping for energy on the grid by 2035, and grid electricity seems like their most promising market.
Woohoo! All right, now everybody unmute yourselves. Clap vigorously.
Thank you.
Woohoo! Malcolm. There's a couple of questions in the chat, and then people feel free to raise your hands for more questions. We're going to do about 10 minutes of that and then go into breakout rooms. So
Okay.
The first one is by Edward. Edward, do you want to read your question?
When you say a couple of questions, there are 73 questions by my count.
Well, no, there was chats going on.
Okay, good.
So yeah, I think let's go with Edward first.
Sure. I was just curious whether there was any long-term issue with the rare earth materials used in some of these magnets if we needed to create a whole lot of fusion power plants.
Yeah, I'm not sure about that. It's definitely a good question, and I think to some degree we don't know, because we haven't been looking as hard for these things as we would if we had a real industrial base that was trying to use them. We also just don't know how we're going to make these magnets in the end, so we don't actually know which elements we're going to be looking for, but it's a big question.
Awesome. Oleg, your question's next.
Yeah, but I'm thinking, and I think I know the answer. Basically, the idea was that use the renewable energy as a secondary just to feed fusion production, production of energy from fusion. How that math is looking.
I'm not sure I understand. What would you use the renewable energy for fusion?
For the power input.
Picture fusion competes with renewable, but I kind of switch those things and I make fusion as the only source of the power for consumers. And renewable actually feeds fusion production. But I guess I know the answer because you said
do you mean
production is cheap? Yeah.
Well, do you mean, so fusion takes energy to run. And so at first I thought you meant the energy that goes in to make the fusion happen would come from renewables, right. But maybe you mean producing the fusion equipment.
Yeah, kind of use renewable as a cost of, to offset the cost of fusion, production from fusion.
Yeah, so the way I think about this is renewable energy is really cheap if you can deal with the intermittency of it. You could deal with it by having cheap storage, or you could deal with it by using it to power a process that is low enough capital cost, high enough variable cost that you don't mind turning that process off when the renewables are not producing. So If it turns out that direct air carbon capture and sequestration equipment is low capital cost, high operational cost, or high variable cost, then that's great. We can run that off renewables. If it turns out for some reason that producing fusion power plant pieces is low capital cost, high variable cost, then maybe that's a good thing to run off renewables. Actually running the fusion reactor off renewable power doesn't make any sense to me, because the fusion reactor is producing electricity that has the same firmness versus intermittency that we want to use to run the fusion reactor. And so I think that that's always going to be cheaper. I mean, if fusion is competitive at all. If it's not, then we can just forget about the whole thing.
Interesting. Thank you.
Stanley, did you have a question?
Yes. Well, basically just two things. Number one, how closely have you tracked, or has your team tracked the developments of, let's say, the national academies? Because I've seen a very similar report about the roadmap of fusion, like a few months that came out a few months ago, as of late 2020, early 2021. And how familiar are you with the fusion industry, I think, associates, or I paid
Fusion Industry Association.
Yeah, that association. I would like to learn about, let's say, your interpretation of, let's say, the dynamics within the ecosystem, because my impression is that fusion, like a lot of other forms of energy, while there's a lot of promising things, it's also, despite the change in funding patterns with, let's say, ARPA-e, it's still competing for finite amount of funds with other forms of energy, right? So I would like to hear more on your thoughts on that, the dynamics.
Yeah, well, so as far as the National Academies report goes, I think one big difference there is no one in government is willing to come out and say what I'll say in a video chat with 41 people, which is, I don't think we should be funding either. And if you go and hang out socially with fusion people, a really fun way to make them uncomfortable is wait until you have a group of them gathered around in a circle, and you're like, guys, thumbs up or thumbs down, should we keep funding ITER? Basically, none of them are really excited about it. None of them see it as a way forward, but none of them wants to be like, let's kill that thing, because they think it's just a house of cards and that all their funding is going to go away when that happens. So that's the big difference. I think the National Academies people are, like me, kind of skeptical about these timelines, and also excited about some of the smaller options. The Fusion Industry Association is compelled by its membership, which is fusion companies, to really toe the aggressive line about we're close, it needs to happen now, that kind of thing, rather than saying, are we ready? Maybe some of these things should happen a little bit later. So yeah, it's a mouthpiece for the companies and says what they wanted to say. Yeah.
Wait, so we're gonna have Peter, Patrick, Micah, Egid, and Konstantin, and then we're gonna cut off questions there and head to the breakout room. So Peter, or Basecamp crew in general.
Great talk, Malcolm, thanks.
Hello.
So my question is related to controls. So it seems like with a lot of these, with all of these concepts, you're basically trying to force matter to condense in one area, and it doesn't want to do that. And it sounds like a lot of the strategies or all of the technologies are basically trying to confine matter to a certain area. And to do this, they're coming up with really precisely engineered mechanical systems to do this. For example, you're talking about keeping the filament kind of in one spot. You're talking about precise manufacturing of electromagnets to confine things. And this is putting a lot of constraints on the mechanical design of these technologies, of these plants. that is kind of the traditional way of designing mechanical systems. The less traditional way is to start integrating more advanced controls to basically release constraints on the physical system so that you can manufacture it more easily, but still get to the end result. So my question is, from the teams that you've seen, do they have adequate expertise on the controls side that would allow them to potentially be more successful, because then they could release these physical manufacturing constraints? Or is this, are the teams not quite there yet in terms of bringing in the controls expertise?
Yeah. Okay, so there's actually a third way that people try to make this work. And I don't think anyone's doing it quite the way you're describing. So you were totally right. There are all these people trying to do this through being very precise about the shape of their stuff. Another way that you can do it is you can try to have a naturally self-stabilizing approach. And ZAP is one of those, where the dynamics of their flow mean that the thing stabilizes automatically. Another one is a company called CT Fusion, which is compact tokamak or toroid fusion. And that's a variant on a tokamak that is also naturally stable. And so they get to avoid a whole lot of types of magnet to keep that guy stable. And then people are treating it as a control problem in some cases to actively stabilize the plasma. So that means, by and large, the plasma in a tokamak is doing what you want it to do. But when it occasionally isn't, then you have software, sensors and software and actuators so that you can detect that it's doing the wrong thing, and you can intervene to try to get it to go back into the state that you want. I'm not aware of anyone trying to do this on a continuous, ongoing basis. It's more, the airplane mostly flies, but we have the computer keep it stable over the long term, rather than the computer is constantly tweaking the wing, otherwise it will crash. I think that that's because if you're not at least stable on the tiny time scale, it's all happening so fast that it's over. Like, people talk about something being comparatively slow fusion because it happens over nanoseconds. So there's just not a whole lot that you can do at the nanosecond scale.
Sweet. Patrick?
Hey, thanks so much, Malcolm. Fascinating talk.
Hello. I just said hello. I don't actually know who's watching. And it turns out it's all friends.
So question, I'm surprised that so early in the R&D process that there are already these concrete projections for what the cost per kilowatt hour might be. And I'm just wondering what the physical, like the fundamental physical limitations are on getting the capital expenditure cost down for this, and whether there's, a long-term horizon for getting the cost from 5 cents per kilowatt hour down to like 1 cent or 1/10 of a cent per kilowatt hour. Is that in the realm of feasibility? Okay,
so I should have clarified. All the numbers that I gave are what the cost needs to be.
Okay.
They're top-down predictions, not bottom-up predictions, if you will. But they're not top-down in the sense of getting to the reactor. They're market-driven, price, not cost, if you will. Companies do their own costings, and I would say they do that with different levels of intellectual rigor. So some of them just really don't understand that capacity factor thing I was talking about, namely, if they run their plant for half the time, they've doubled the cost of electricity. And so they will look at me and they'll tell me, we've calculated our cost of electricity and it's going to be $30 per megawatt hour. And then I say to them, what capacity factor did you use? And they're like, well, it's hard to know because the equipment's not operational yet. But nuclear power plants get to 92%, so we use 92%. And then I'm like, just look at the two halves of this. Look at the we turn off for renewables and the 92%. You don't have both of these at the same time. And then they're like, oh. And then the really sad thing is 6 months later, they're giving a talk and they're saying the same damn thing.
So if they're predicting $30 per megawatt hour, then it makes sense that, that this, would require some level of energy storage. But is there anybody saying we're going to be able to do this for $3 per megawatt hour, so it doesn't matter?
No one has a path to being an order of magnitude cheaper like that. What counts for me as kick-ass fusion, as I call it, meaning fusion that is really crushing renewables on price, would be if you get down to $15 a megawatt hour, that kind of thing. I actually think that ZAP has the potential to get down there, more so than any of the others, just because the system is incredibly simple. Olga, do you want to mute everyone again?
Yes.
Or at least that guy. So in the long term, I don't think we really know what this is going to cost, in the same way that no one thought that solar and batteries were going to get this cheap. But if you look at what's plausible, it's more like, can we get down to the same price as renewables, but now this is firm, and so it's actually much more valuable power. And honestly, that's enough. I think beyond, if we can hit those numbers plausibly with intellectual honesty and not having to say, well, we're going to sell you a 3 gigawatt power plant, and like, we made it really big, that's how it's cheap. But by the way, no one believes we can build a project on that scale, and no one wants to pay $6 billion. If we can avoid all of that stuff, that's great. The rest is really cool as a techno-optimism project. It's just not a climate change project. And like, if that's what gets some investor excited, that's great, but it's not where I've been focusing. And I don't think anyone knows the answer.
Thanks.
Awesome. Igor, you're next.
Yeah, thanks, Malcolm. I'm a little I'm having trouble understanding how the timelines you've outlined overlap with the overall climate change timelines. Okay, 2035 in the best case, maybe 2040, and by that point the world has changed. What's changed about the world in the interim? People have already built giant lithium storage projects, or I don't know what, I'm just trying to understand the world into which fusion will begin to make an impact. How does that, how is it still relevant then? Or what do you think about that?
Yeah, so I think that there's a scenario where we actually get really cheap energy storage and fusion dies on the vine. That's awesome. A whole bunch of people wasted their time and their money, but we saved the planet. There's another scenario where we get up to 30, 60% of the grid coming from renewables. You can do that without the costs of storage biting too hard. And then you get this point where it's really expensive adding more intermittent power to the grid. And then fusion comes along and we deploy that afterwards. That's the, well, depending, optimism is difficult to define in this, but that's the scenario where fusion is relevant. You can also say places like Singapore, Japan, that want energy independence and don't have a lot of renewable options. You don't save the planet off the back of those countries. Those are initial markets. So limited relevance.
And I think it is interesting to see the progress in the last 15 years to compare it to the next 15 years. Now, obviously, we're putting a lot more money and effort into this now. But I think there is in many ways, the world can change very fast, and in many ways, the world changes very slowly. So I think it's worth kind of in some ways doing a survey of kind of what are people projecting and what happens faster than projections and slower than projections. So it's been, I don't know, it's kind of a fun game that I play with myself.
What would happen if Elon Musk started a fusion company?
Right. All right, and the last question, Konstantin?
Yeah, I think my question is very similar to Patrick's. So you mentioned at some point that fusion plants would have high capital costs as opposed to, let's say, natural gas plants, right? So the generation part, I assume, is very similar. So what drives the difference? What makes
between fusion and natural gas?
Yeah, what makes the fusion plant so much more expensive?
Oh, the only part that's similar between fusion and natural gas is that eventually there's a turbine with an expanding gas or fluid going through it that makes it spin, and then we get electricity. Natural gas has basically nothing before that, right? We just have gas and a flame and then whoosh. Fusion needs to have a bunch of equipment to take deuterium and tritium and get them really hot and pressurize them. So we have some heating equipment, we have some magnets to pressurize them, and then we need equipment to absorb the neutrons, and we can't absorb the neutrons that well into the gas that's then going to heat up and drive the turbine, so we're absorbing them into some sort of molten salt, and then we have to heat exchange the molten salt into water or supercritical CO2 to drive the turbine. But then also the molten salt ends up with tritium that we made when the neutrons interacted with lithium and lead inside the molten salt. So we don't have enough tritium to treat that as a fuel. The fuels are deuterium and lithium. And then, so the lithium gets used up in this process that converts lithium plus neutrons to tritium. So now we have the tritium coming out in the molten salt. So we want to use the molten salt to heat exchange to drive the turbine, but also extract the tritium. And then we didn't burn all the tritium and the deuterium that we put in. So we need to extract those from other waste products like helium and any burned up bits of first wall. And so we got all of these. We need to separate out the deuterium and the tritium. This is basically and like an isotope separation. It's not basically, it's literally isotope separation. So that's tricky and expensive. And one of the many problems that have not been demonstrated at the commercial scale or cost. And then tritium is somewhat dangerous to people. It's okay outside your skin. It's dangerous if it gets incorporated into your body. So you need to prevent the tritium from leaking out, but tritium is just hydrogen. It's just a proton and a neutron, two neutrons. And so it permeates through metal walls. And so if you have a container filled with hydrogen, it's leaking hydrogen and no one cares. If you have a container filled with tritium and it's leaking tritium, people do care. So there's this whole complicated chain going on to produce heat. And you can view fusion cynically as, okay, what a complicated, expensive way of making heat. There must be a better way. But you look at all the other options and you're like, well, I don't really see a better way, so I guess I'll keep looking at fusion.